Go ahead. Go ahead.
Okay. If you hear me,
Yes, everything is fine.
okay. Okay, now I can start. I would like to present some highlights of our recent work on the polaron theory, accounting for nonlinear interactions in a non-parabolic band. This work is performed in collaboration of three teams: Jacques Tampere and Matthew Output from University of Antwerp, Belgium, Cesare Franchini, Stefano Rani, and Thomas Hahn from University of Vienna, and Andrei Michenko from Institute of Physics, Zagreb, Croatia. Please tell if you hear me.
Yes, everything is fine. Go ahead.
Okay. This talk is devoted to some highlights of our recent work in polaron theory, accounting for nonlinear interactions. Traditionally, polaron is considered as a particle interacting with oscillation of the crystal lattice, and oscillations in the harmonic approximation are naturally considered as small oscillations. But this approximation sometimes requires to go beyond this linear and harmonic approximation, because nonlinear terms in the electron-phone interaction can be important in some observable properties. For example, it explains the unusual dependence of resistivity at high temperatures. For example, the other highlight, the other example is an explanation of the superconductivity transition at very low concentrations in strontium titanate. It was explained even before in the linear harmonic approximation, but nonlinear terms lead to much better agreement with experiment and more convincing predictions, especially in the limit of very, very low concentration. This is the reason, this is motivation, or partial motivation of our work. I would like to present here two examples of our work. First, we consider the quadratic interaction with TO phonons in polar crystals, such like strontium titanate, which where the interaction is considered as two terms: the usual Fröhlich interaction and the quadratic interaction, which was introduced many years ago in the phenomenological form, where the coefficient describing the coupling strength is just phenomenological constant. And as a result, you obtain the Hamiltonian with Fröhlich interaction with LO phonons and quadratic interaction with TO phonons. This model was already used to explain experimental data on the anomalous dependence, temperature dependence of the resistivity in quantum paraelectrics, in particular in strontium titanate. And we apply here the extension of the Lillow-Pines method for stronger coupling, which was first proposed a long time ago, but now it was renewed. The interest was again grown because of its applicability to quadratic specifically suitable for the quadratic interaction, and especially for non-parabolic bands. But the first example is a TO phonon quadratic interaction in parabolic bands. In order to emphasize the effect of the quadratic interaction, we consider first the purely quadratic contribution to the polaron energy, separating it from the Fröhlich contribution, which is already very well known. And in order to apply this method of the so-called squeezed phonon state, the three canonical transformations are performed. First, two Lilov-Pines transformations, and the squeezing transformation of Bogolyubov-Tyablykov, which mixes the annihilation and creation operators of phonons. It was the procedure of the obtaining the polaronic shift of this quadratic contribution to the energy is very well established, but it appears that it was very well established for the linear interaction, but it appears that the quadratic interaction enters this procedure in very, very natural way. And first we obtain the ground state energy of the so-called quadratic polaron using the model interaction with the soft TO mode, phonon dispersion, as in recent work by Maslov, which I already mentioned. But this method, of course, requires a cutoff for the momentum, which is associated with the Brillouin zone. And we compare our analytic calculation, result of our analytic calculation, with the result of partial Monte Carlo summation of our colleagues from Vienna. And we see excellent agreement in what regards the ground state energy. The other parameter which is interesting for this model in parabolic band is the effective mass. And it is not surprising that for negative values of the coupling strength, the effective mass exhibits divergence, which must be attributed to the polaron instability or instability of the crystal lattice for sufficiently large negative values of the coupling strength. Physically, it is very clear because the quadratic interaction is some very far analog of the contribution to the phonon energy. It's also quadratic. And if the negative quadratic term is sufficiently large, the phonon system will be unstable. So it is manifested in a divergence of the effective mass. So strictly speaking, the physical sense can be attributed only for the coupling strength above this critical value. More clearly, it will be shown in the next example of our recent work on polaron, where we consider polaron with purely quadratic interaction with some scalar field in a non-parabolic finite width band, which is modeled by Titan binding model. Tight binding model. It was already published one paper in the past year where this polaron was considered by Monte Carlo calculation, and now we added some analytic results in order to compare how our analytic method works. So it considers the free electron energy, the free phonon energy, and quadratic electron phonon interaction. And next we go to the momentum representation for a single polaron in order to apply the squeezed phonon states approximation. And next, apply two subsequent Lie-Low-Pines transformations. And what is remarkable, what is new in this approach, that we successfully applied this Liouville transformation to the non-parabolic band, a finite width band, completely keeping the translation symmetry, the structure of the symmetry of the Brillouin zone, the correct boundary conditions at the Brillouin zone. And after this transformation, we arrive to the coordinate-free polaron Hamiltonian, and then apply the squeezing transformation to this Hamiltonian. And after this, we obtain again the complete spectrum, the momentum-dependent spectrum of the quadratic polaron, and compare it with the results of the Monte Carlo calculation in different regimes. So this Hamiltonian, which proposed by us in this task, embraces, in fact, all polaron regimes. For example, the adiabatic regime where the phonon frequency is small with respect to the band width, it is in fact close to the limit of the large polaron in the effective mass approximation when bandwidth leads to infinity. And the other limit, the anti-adiabatic limit, describes the rather small polaron than a large polaron, with the same, of course, with the same structure of the electron-phone interaction. And here we compare our analytic results with the diagrammatic Monte Carlo data of this previous paper, and which are shown here, and with the weak coupling approximation, the perturbation theory, and this is the result of the squeezed phonon states approximation. We see that, of course, the squeezed phonon states approximation, as a will opines, works well, especially in the range of weak coupling than in the range of large coupling. And this range of considered coupling strength is very large. But in any way, we see significant difference between the weak coupling regime and the squeezed phonon states approximation. And it at least qualitatively well reproduced the, especially in the not very large coupling, the Monte Carlo result. Also, we consider opposite limit, the anti-adiabatic regime, where the phonon frequency, phonon energy is rather large with respect to the bandwidth. And here we see the excellent agreement with the Monte Carlo results, because it's in fact it's close to the exactly solvable model, the so-called atomic limit. All three results lie very close to each other. So this excellent agreement explains that the coordinate-free Hamiltonian in the atomic limit is an exactly solvable model which can be exactly diagonalized by the Bogoliubov-Tyablykov transformation. Also, please, I will would like to show also two more results about the effective mass. For the effective mass, we see, of course, not so good agreement with the Monte Carlo data, but qualitatively it agrees. The result for the adiabatic regime. And here we see that it's underestimates the polaron mass, and that needs further improvements. For example, accounting for the terms beyond the truncated quadratic and linear. And this is the results for the anti-adiabatic regime. We see here the very good agreement in the small and negative values of the coupling strength. And we see here the same divergence of the effective mass as predicted by Monte Carlo, and which physically follows from the instability of the crystal lattice at sufficiently large negative coupling strength. And next, it is of course interesting to show the total dispersion of the quadratic polaron along some standard paths within the Brillouin zone. When we consider two opposite regimes, the adiabatic regime and the anti-adiabatic regime, we see that in the adiabatic regime, the momentum dependence of the polaron energy is a bit more complicated than for the bare electrons, which correspond to the coupling strength 0, especially at sufficiently large momentum. And in what regards the anti-adiabatic regime, the dispersion, the polaron energy is expressed mostly by the total shift of the conduction band as a whole, because the band is rather narrow, and this means that in fact the effective mass in this regime is not very important parameter, because in the atomic limit is it completely loses its sense. So, and what is remarkable that this squeeze-form states approximation allows us to, again, I repeat that it exactly takes into account the translation symmetry of the polaron in a non-parabolic band, and consequently it accounts for the correct boundary conditions in the Brillouin zone. So now I can conclude that this method of squeeze-Ponon state looks very promising for the treatment of a polaron, analytic treatment of a polaron, and to compare results with purely numeric calculations. So as a whole, this work is just a collaboration of the numeric calculation team from Vienna and Zagreb, and our small group which performs analytic calculations in order to show that analytic calculations can be still valuable and promising for future applications. So I think all. Thank you very much for your attention.
Very much for your talk. So do we have a question from the audience? Still, you have like 10 minutes. So we have 10 minutes for discussion. So please, yes, go ahead.
I use the microphone or?
Yeah, it's always better with microphone. We have 10 minutes for discussion. Go ahead.
Just a small question, because the matching with the numerical methods is really strong. What was the software that you used for the simulation? Some diagrammatic Monte Carlo? Which were the software that you used?
Sorry, it's
Louder.
Sorry, which is the software that you use for the simulation? In previous
So
slide.
if can I stop share and just maybe hear you better? Sorry.
Yeah. Yeah, so what is the software that you have used for simulations? What type of software?
Yes, but this is a so-called WASP package, but it is not our team. It is Vienna team. Our colleagues from Vienna use the so-called WASP, Vienna VASP, it's abbreviation, package for the numerical calculations, Monte Carlo.
So what's the essence of numerical method that was used? What's the type of algorithm that was used? It's Monte Carlo, right?
This is diagrammatic.
Diagrammatic, I see. Yes,
Diagrammatic Monte Carlo.
Thank you so much, and also appreciate that you have the in your presentation you have the time controls, and I'm really jealous of knowing how to do that, to put the time in the presentation. Oh, sure.
Okay, so question is, you said about non-parabolic potentials, right?
Yeah, non-parabolic band.
And can you be more precise than just saying non-parabolic? Can you specify a little bit the class of functions in more detailed way?
For a non-parabolic band, here is a simple tight binding model. Just trigonometric functions.
Okay. Question is also what type of materials you can tackle with. If you can refer to very specific compounds, your model, how you can test your model experimentally.
First of all, we consider such crystals like strontium titanate, where the nonlinear interaction is shown to be really important. But it is not narrow band, but rather intermediate width band, but non-parabolicity and finite width is important also there. Strontium titanate and also other perovskites, maybe.
Okay. All right. Do we have any more questions from the audience, maybe from Zoom audience? Yeah, so from this audience. All right. If we have no questions, thank you for your talk, and let us move to the next presentation.
Thank you for the invitation.
My pleasure. All right. So